Greetings once again, acolytes of the celestial Emacs. The state of work is good. Through the creation of tools, we have enabled our LLM to perform recursive transitive lookups through multiple sources of documentation and source code and high-level indexes to answer queries about code based on facts that it has read, not just the Stack Overflow data embedded in its weight matrix. And this can synthesize, summarize, and translate simultaneously. What a time to be alive. Welcome to Emacs at Lunch. To keep it short, this video is going to focus on creating tools and some of the insights gained while prototyping tools for the demos. So what is a tool? It's a combination of a function that we want the LLM to call and an interface declaration that tells our stringly typed natural system how to try to call it with a reasonable success rate. When would I want to declare a tool? The first case is if I don't know if I want to call a function and I need to rely on the AI as a heuristic to decide when to call it. The second case would be if I don't know which function I want to call, and in this case we're using the AI as a heuristic to decide our dynamic dispatch. In the third case, I might need a heuristic to decide which input to give to the function. I'm using the AI to decide the arguments. In the fourth case, my AI may carry out a lot of steps, it may produce a lot of output, but then at the end I need it to decide which part of the output is actually the result. All of these cases can occur in composition. We may have a process that has multiple steps where at each step we have to rely on the AI as a heuristic to decide which function are we calling, what are we calling it with, and what are we doing with the result. The place where we probably don't need a tool is if we're giving some input to the AI that is configured to always carry out a specific transformation, and the result can be produced in one step, so we don't need the AI to adapt its output into a more structured response. So how do we build a tool? Like I said, it's just a combination between a function that we already know how to write and an interface that we just need to learn how to declare. A basic tool declaration consists of some very obvious parts. We're going to have a function that actually gets evaluated. We'll have a JavaScript style name that we can refer to in the system prompt or the user prompt or inside of other descriptions. And then we're going to have some arguments that tells the LLM how to provide input to our tool. And then we'll have a description that tells the LLM kind of how to use this tool. It's like a miniature system prompt. It's kind of like a doc string for the LLM. Focusing on the arguments, the first thing we can see is that they are positional. The second argument in the function signature corresponds to the second argument in the args list of the tool spec. There can be more than one argument, so args is a list. Each argument has a JavaScript style name, a type, and a description. The important thing about the description is to line up with the description of the tool, which we'll talk more about later. The arguments the LLM gives our function is deserialized from JSON, so you need to be aware of which JSON types correspond to which Elisp types. The only kind of special cases are that because we're mapping nulls to nil, we're mapping the false in JSON to the keyword symbol JSON false. And then when we get an array, we're mapping that to a vector. Here's some literal values that might be a little bit easier to see. I've tested every single one of these types in the tools developed for the demo. If you want to receive a little bit more structured data, you'll have to set a properties key that describes the structure that you expect, and then you have to set a required key to tell the LLM which fields cannot be null. Realistically, I'll do this whenever I'm handling an array of inputs and each input needs to have its own individual attributes, like if I'm creating a list of pixels and each pixel has an individual RG and B property. If you want to receive an array, you just need to specify the items type. We use a full plist for the items because we can do things like having nested arrays. To receive a choice from a specific set, we'll use an enum type. You just set the type to string and then set the enum field to a vector of the possible string choices. And finally, while we want symbols, whenever we're introspecting Emacs and Elisp itself, to obtain a symbol, just accept a string and pass it through internSoft. InternSoft will only return a symbol if that symbol already exists, which can save us from accidentally creating symbols from the hallucinations of the LLM. That's most of the special cases for input. What do we do with output? The short answer is that the GPTel backend is going to coerce almost everything to a string anyway. Even the APIs that advertise support for things that are not strings are probably just serialized them into the context. They may have some special training for handling objects, but this varies by model and API, and whenever the API can't handle a type, we'll have to coerce it to a string anyway. You might as well coerce it to one that you think will make sense. The easiest way is to just return literal JSON answers. If there's no answer, you can return a literal string of null. For Boolean answers, you can return strings of true and false. And for magic values, you can just return strings of the literal JSON value. All of the models available today train a lot on JSON, so passing back a serialized JSON value is never a bad idea. You just need to convert your Elisp types to the types that can be mapped back to JSON. That means if you have a list, you'll probably want to pass it through vconcat before serializing it. If the Elisp structure you have is already meaningful on its own, you can just call print1to-string to send a representation of that. That is the same as the fallback whenever the type is unsupported by the backend. And finally, if you need to error or the functions you call error, just try to make sure that the messages are meaningful to the LLM so that it can try to recover. There are some specific settings in use to JSON serialize and JSON parse string that enable them to perform consistent conversions. These two functions together form an identity. Whatever you put in, if you call both of these functions in either order, you will get the same thing out. Once you've written a function and figured out how to specify your arguments, you just need to package it together into a tool with the GPTel make tool function, and then you need to add that tool to the GPTel tools list so that it'll be active. Once a tool has been created and added, you can see it in the GPTel chat interface, and you can also see it in the GPTel menu under Tools. To test it out, just ask the LLM to call the tool. It knows the tools by the names that you gave them. If I need to do something slow that would block the Emacs UI, I can instead make an async tool. The difference is that an additional first argument will be passed in that is the callback. After I finish doing my slow operation, I will use that callback to return the result. The confirm option is a good idea whenever your tool could do something very dangerous, like deleting files or leaking secrets. GPTel has a global setting that is by default configured to auto, meaning let each tool specify whether or not it will confirm. The default for each tool is to not confirm. There is also an option to include the results. This will write the results of the tool into the message log. Setting this enables the LLM to refer back to previous tool results. This is absolutely essential for retrieval-augmented style use cases where we're building up a context through multiple rounds of discovery, and it also enables a combination of step-by-step behavior in conjunction with tool use. All of the most compelling prototypes I've put together so far extensively use include. It is the reason why I focus so much on the explicit-tool-turns PR to be sure that we had first-class treatment of tool messages in the message log. The only time when I would not use include is when the resulting behavior is embedded in the LLM's decision immediately following the use of the tool. So if the LLM is leaving behind a trail of evidence about what decision it obtained from the tool call anyway, then it's not going to need that result in the future. Very closely related to including tool results in the message log is the description. It is very easy to overlook the description and think that it's for us. It's not for us, it's for the LLM. It's like a miniature system prompt, and a system prompt is kind of like a program, and the most critical behavior in that program is how the functions connect with other functions. The LLM is kind of like glue, but you want to specify the edges connecting the various tools together. After I call this tool, which tool can I use on that result? In all of the most compelling prototypes I've put together so far, they include almost more program in the description than there is in the function that's being called. Almost all of them are including tool results in the message log, and almost all of them are specifying how to use those results in follow-on functions or recursively to continue stepping through to a solution. So what I'm going to emphasize for today is that you really want to focus on how the descriptions fit together with each other, how the descriptions fit together with the system prompt, which could change depending on which operation you're doing, and how the data that you're putting into context through these included tool calls, especially the tools that you recommend the LLM starts with, continuously point the LLM in a direction of making progress towards the eventual goal. We're going to pick back up with the configuration of GPTel, including the customizations that I made for the PR that I have open. So be sure to subscribe and then like and share, because we're at around 2,500 subscribers. There's about 50,000 on Emacs YouTube. The GitHub sponsor support is about to cross 2%, and if it gets up to 10%, it'll be very easy for me to continue investing in these AI integrations for Emacs and to continue developing PrizeForge. All of the notes for that configuration, the configuration itself, and the source code for the 22 prototype tools is available on my private GitHub. You can check it out for $1. If you like what you see, buy me a hamburger. I can buy LLM tokens with hamburgers. I'll even share a picture of the beautiful hamburger. Peace.
Whoa. Not bad, partner. Follow me. I'll cover you.